And maybe the most important speaker here is Claudia Schillings, and a co-organizer of this workshop. She's going to talk about the convergence of Laplace approximations and its implications for Bayesian.
Okay, thank you very much. So the work I present here is joint work with Björn Sprung from the University of Göttingen and Philipp Becker from the University of Erlangen. So what's the setting we are interested in? What we want to do is we are interested in a setting where we have a small noise covariance, so we have small noise in the observational data, or we have large amount of data. So that means we have to work with a very concentrated posterior. That's very much the setting of the previous talk. So for example, in design of experiment, you are very much interested in a concentrated behavior of the posterior, because it means you have informative data and you can infer your parameters. So what we want to do is, or what you can see is, sampling methods will suffer from this concentrated behavior of the posterior. So that means we have a deterioration of the convergence behavior of our sampling methods, and we are interested in removing the degeneracy coming from this concentrated behavior of the posterior in the integral, just by using preconditioning techniques based on Laplace approximation, and show then that the resulting methods based on this approximation can be robust with respect to the size in the observational noise. So that means we don't have any influence of the size of the observational noise on the performance of our methods. So that means here's the outline of my talk. First of all, I would like to introduce the setting, so the Bayesian inverse problem which we want to solve. I will present a short motivational example where I will show you that sampling methods will indeed suffer from small observational noise. And I will show you that using Laplace approximation, we've heard about Laplace approximation a bit in the previous talk, that Laplace approximation can be used as a preconditioner in this setting in order to remove the degeneracy, so that we have a behavior of the sampling methods which is robust with respect to the size of the noise in the observations. Okay, so short motivational example. Then I will say a few words about the computation of the Laplace approximation, because we've heard that gradient evaluations are involved. So I will shortly comment on how to efficiently compute the Laplace approximation in our setting. And then the main part are the approximation results. Here we are interested in approximating or bounding the difference between the Laplace approximation and the true posterior, which can be then used in order to analyze our sampling methods. Okay, and as usual, a short summary and outlook. Okay, so this is the setting in which we want to work. So the inverse problem is the usual one. We want to find unknown data from noisy observations. U is here the parameter function. G is the forward response operator mapping from the parameter space here, capital X, to the observation space. We have that Y denotes here the observations. We assume that we have a finite number of observations. So capital Y is here just Rk, where K is the number of observations we have. We should have in mind that usually one evaluation of G is expensive in our setting. We assume a prior distribution denoted here by mu naught, and we have a noise model. So we assume here additive Gaussian noise, which is normally distributed with zero mean and covariance operator or covariance matrix in this finite dimensional setting gamma. Okay, so we are interested in the setting where this one here goes to zero. So we have small observational noise, so highly informative data, and therefore a concentrated effect, concentrated posterior in our inverse setting. All right. Okay, so then just by Bayes' theorem, we have that the posterior distribution can be expressed as the Radon-Nikodym derivative with respect to the prior. We have here that phi denotes the misfit potential. We have that the norm here is weighted by the covariance matrix of the noise, and Z denotes in this talk the normalization constant. So we have the normalization constant here in front. Okay, so that's the setting. The algorithms we are interested in, first of all, Markov chain Monte Carlo methods in order to sample from the posterior distribution. There are dimension robust methods available, so that means we can use it in infinite dimensions. We have multi-level strategies in order to enhance the performance of MCMC methods, but MCMC methods suffer from a concentrated posterior, so the performance will or the convergence rate, the computational performance, I should say, because you can prove convergence rate, but the computational performance deteriorates with concentration of the posterior. The same for important sampling or ratio estimators. We've heard a bit about ratio estimators in the talk today in the morning, or also in the talks yesterday by Christoph Schwab or Rob Scheike, for example. For the ratio estimators, we can use Monte Carlo approaches, quasi-Monte Carlo methods, higher order quasi-Monte Carlo methods, or also sparse grids, so deterministic quadrature methods. Again, there are dimension robust versions available, so we can show for those methods that we have a convergence rate independent of the number of parameters which we want to identify. Again, we have multi-level strategies in order to enhance the performance. But again, as we will see in a minute, those methods will suffer from a concentration effect of the posterior. And the idea is to somehow do a preconditioning step so that we can show that preconditioned versions of those methods here are robust with respect to the noise in our observations. Okay. So that's basically what I just said. So why are we interested in the small noise or large data limit? Well, we have a concentration of the effect of the posterior. We have a non-robust behavior of our sampling methods with respect to the noise in our observations. But on the other hand, in practice, it's really a highly desirable situation because it means we can identify the unknown parameters. So you're really interested in this concentration effect of the posterior. And also, of course, in the setting of design of experiments, that means you have highly informative data, and that's basically what you're looking for. So that's the goal of your optimization step. So that means we need methods for this setting. And the idea is to analyze methods which are robust via preconditioning using Laplace approximation. So this is, of course, a widely used approximation in practice. We've heard that it's widely used, for example, for design of experiments. It's also used as an approximation of the posterior distribution. So you just use Laplace approximation instead of the posterior for integration purposes, for example. What we want to do here is use it as a preconditioner. That means we want to use it in an important sampling context. Okay. Before I show you the example, let me first introduce what Laplace approximation is in this setting. So first of all, we have to assume here that we work in the finite dimensional setting. So I have to truncate, for example, if I work with a Caron-Löw expansion of my parameter function, I have to truncate so that I work in the finite dimensional setting. So X is here assumed to be RD. So then I can work with Lebesgue densities. So I denote by pi naught the Lebesgue density of the Fourier measure, and I want to work with this function here, which capital I, which is just the negative log posterior density. So we have phi is the quadratic misfit of the Radon-Nikodym derivative, and we have here the log of the Lebesgue prior density. Okay, assuming that this function here is smooth enough, then Laplace approximation is given by this Gaussian measure here, which is, or where the mean here is just the map estimator. So that means this one here is the minimizer of this functional capital I here, minimizing over the support of our prior distribution, so the support of the Lebesgue density of the prior. And we have that the covariance, or the inverse of the covariance, is just the Hessian at the map estimator. Okay, so that's Laplace approximation, and that's what I want to use in order to precondition my computations. All right, so here's my very simple test example, just to show you what the problem is. So we have here our toy example. We have seen it several times. Here it's even simpler. We have just one one-dimensional problem, so physical domain is 0, 1. The diffusion coefficient is assumed to be log normal, so we have a parameterization of this form here. U1 and U2 are just normally distributed, and we have two ansatz functions, psi1 and psi2. Okay, so what's the inverse problem? Well, we want to identify our unknown parameters given observations. This one here is the quadratic misfit functional. We are interested in the behavior if the noise in the observations goes to 0. So what I do here is I just parameterize the noise. So I assume it's equal to lambda times the identity matrix. So lambda is here just 1 over n. So n goes to infinity. That means lambda goes to 0, and I have vanishing observational noise in this setting. Okay, so this here is then the negative log posterior Lebesgue density I have to work with in order to compute the Laplace approximation. The quantity of interest, I assume I would like to compute the integral of a quantity of interest with respect to the posterior. The quantity of interest in this setting here is just the solution at the midpoint in my physical domain. And I have two system responses. I have two observation points I use at 0.25 and 0.75. Okay. Now, to give you an idea how it looks, how the posterior looks like in this setting here, so what we have here are contour lines of the negative log posterior density. So this one here is the true parameter. First of all, with a large observational noise, what we can see here is, well, we don't trust the data because we have a large noise. So basically what we see here is the prior distribution, okay, because the noise is too large. I assumed Gaussian prior for our two parameters, U1 and U2. So what we see here, prior, almost the prior. Okay, then decreasing the noise, we can see that, okay, now we trust the data a bit more. We move towards the true parameter, and we have a strong concentration effect as well. So what we have here is now a very concentrated posterior, concentrated around the true parameter because I assume that there's no model discrepancy, for example. Okay, so that's what you want to have in order to have consistency. Okay, so concentrated behavior is getting even worse when the noise is smaller. Okay, so that means using now sampling methods in order to compute an integral of a quantity of interest with respect to this posterior distribution here, we just sample according to our prior. So we have to sample in this whole space here, and as you can see, so for example in this region here, there's almost no information about the posterior distribution, so it's almost 0. And we have to somehow identify this region over here where all the posterior mass is in order to get a good approximation. Yeah.
It's not just a rescaling problem. If you already know that you have a parametric convergence rate, you just rescale your posterior with the inverse feature information, and then you know.
Exactly. So that's what we want to do. So we use Laplace approximation, which is basically what you suggested, in order to remove the degeneracy. So that's exactly Laplace approximation, what we want to use, and that's what people do. And the idea is to show that we are indeed independent on.
I mean, if I understand, I don't know why it's called Laplace approximation, but you're actually computing, in this case, a normal, you sample from a normal distribution when you use the Laplace approximation. Is that right? Or?
Yeah, so what we want to do, let me just go to this slide here. What we want to do is use Laplace approximation, so we don't want to use the Fisher matrix, but we use the Hessian second order information at the map estimator in order to approximate the posterior distribution, but we don't want to use this Laplace approximation instead of the posterior distribution, but we use a rescaling according to exactly this distribution. Of course, this is just a very simple test case now where almost everything is almost Gaussian, I would say, so it's very straightforward to use it, I would say, but you can show it in a much, in a more general way, I would say. Yeah.
It's worth pointing out that in classical statistics, it's often referred to as a saddle point approximation, and that the same sort of saddle approximation goes back deep into applied mathematics.
Yeah, definitely. So I don't want to say that we invented the method to so it's just we want to analyze the Laplace approximation, but yeah, there are several.
I would call it just like a Bayesian saddle point approximation.
Yeah. Definitely. So it's used in many ways already in the statistics community, but also in the applied mathematics community in order to precondition everything in order to get a better, a well-posed problem if you want to. What we want to do now is use exactly this approximation in order to show that methods can be robust with respect to the observational noise. So that's the idea, basically. Okay, but so as you already said, so that's basically the idea which we want to use here. Laplace approximation in order to remove the degeneracy, so what we use here is the preconditioning or transformation according to the second order information. So what we do is in the preconditioning step, we just do a translation to the map estimator and precondition according to second order information. So that's the idea of the preconditioning step. I say preconditioning, that's a word stemming from the applied mathematics community, but you can think of it as an important sampling, what we do here, because we integrate now our quantity of interest, which we want to integrate with respect to the posterior, not with respect to the prior. That's what we would do in the generally in the basic setting, but we use Laplace approximation and then have here the important sampling rate, so just the derivative of the posterior with respect to the Laplace approximation. Okay? What I would like to show you is the performance of importance sampling, or just in the basic variant Monte Carlo for the ratio estimator, quasi-Monte Carlo for the ratio estimator, and just a deterministic quadrature rule. Since we are working here just in 2D, I use the tensor grid, so no need to do sparse grids. And we use it for this integral here, so we integrate in the basic variant everything with respect to the prior, and we use in a second variant the Laplace approximation in order to investigate the performance for our preconditioned method. Okay, so first of all, here is what we have been transforming according to the Laplace approximation. What we want to have in the end is standard Gaussian. What we have for an observational noise of size 1 is almost a Gaussian, so you can see that we have the contour lines are ellipsoids. So Laplace approximation, there's a difference between Laplace approximation, still a slight difference between Laplace approximation and the true posterior, but then for smaller noise it's just almost standard Gaussian, so the error is very small. Okay, so what we have here now for the numerical performance of our methods is the following. Here is just the standard method integrating with respect to the prior, with respect to the size of the noise. So we have Gaussian mean, importance sampling, or Monte Carlo for the ratio estimator, and quasi-Monte Carlo. What we can see here is the nice performance in the beginning for a larger noise, but then we see that we can observe the numerical instabilities because we can't compute an estimate anymore for a noise below 10 to the minus 5. Okay, so there's a blow up because of the numerical instabilities, whereas when we precondition, that means just the translation by the Laplace approximation, we can see a very stable behavior of all the methods. Just to give you an idea of the performance of importance or Monte Carlo and the transformed, the importance sampling for each noise. So what we can see here is the performance with respect to the number of samples, root mean squared error here for the different sizes of the noise. We have the expected convergence rate of importance sampling for the larger noise variances, but then we can see that we have a deterioration of the performance. This is, of course, you still have the convergence results, but the problem here is that due to the concentration effect, you don't have that much information from the first samples, and you have to sample a lot in order to identify the region where the posterior concentrates. Okay, so that's why we have this deterioration effect here for smaller noises, and we have no convergence at all for noise below 10 to the minus 5. Whereas for the transformed one, well, this is a very simple example. This is exactly what we expected. We have this very nice convergence behavior, so no influence of the noise. need what you can see here. It helps us because we have a smaller variance. Okay. The same also for quasi-Monte Carlo, the same behavior also for the transformed integrand. Okay, as you already said, that's not surprising, but what we want to show is that indeed we can prove we can use results on the difference between the posterior and the Laplace approximation in order to analyze our methods then in the end. Okay. As I said in the beginning, we have to compute Laplace approximation, and I just want to say a few words on how to efficiently do that, because we need the map estimator and we need second order information. We don't want to compute second order information explicitly, but what we do is we use a trust region quasi-Newton approach with symmetric rank 1 updates. Okay, so we use a second order approach here in order to be efficient. So we have superlinear convergence of those methods here, and we use it with a very specific update formula in order to approximate the Hessian, because we know that those update formulas, the symmetric rank 1 updates, they converge to the true Hessian. Okay, so that's not true for like BFGS updates, but for this one, under suitable assumptions, of course, one can show that we converge to the true Hessian, and we don't need to approximate the Hessian in the end after the optimization at the map estimator. So it comes for free from the optimization strategy. And then this here is what you suggested. So we use the transformation, so we use just the translation by the map estimator, and here in front of we have a rescaling according to second order information at the map estimator. Okay, so that's exactly what's done in practice, I would say. Okay, now of course, since it's a gradient-based method, we need gradients in order to do the optimization step. But it's worthwhile to do the optimization step, because using second order information, you usually just need a few iterations, like 20 iterations. Yeah, so that's nothing compared, of course, to the computational effort of your sampling method. So you have to do it a priori, so in order to get the map estimator and the Hessian information, but just 20 iterations, which means 20 forward simulations, it's very cheap. Okay. Then what's about the gradients? Well, in PDE constraint optimization, you have an approach, the adjoint approach, in order to compute efficiently gradients. And the adjoint approach is again computing gradients with the adjoint approach is independent on the number of parameters which you want to identify. Okay, so it's very efficient. What you have to do is you have to solve a second PDE in order to get the adjoint variables which you use in order to compute the gradient. So what you have to do is, in each iteration, you solve your PDE, describing your model. You solve another PDE in order to compute the gradient. So you have two PDE solves in order to compute the gradients needed. That means altogether, you have a computational effort of about 40 PDE solves. Okay, so that's very cheap compared to Monte Carlo, for example, or finite differences then, to approximate those informations. Of course, you have to somehow derive the adjoints. Well, you can do it in a continuous way or discrete fashion, but you can also use for more complicated codes, or if you are not familiar with the approach, you can also try to use automatic differentiation, which gives you then the discrete adjoint. Okay, so that's just one slide in order to convince you that it might be worthwhile to use an optimization in front of your sampling or before your sampling method. Okay, now what's about the analysis? I was a bit slow in the beginning, so let me now tell you about our results. So the first one is for uniform priors. We have an asymptotic analysis based on Laplace method. So assuming that all the assumptions of Laplace methods are satisfied, in particular we have that this one here is now the negative log posterior density in the uniform case, that the minimizer is non-degenerate. What we can then show is that we have an asymptotic expansion of this integral here over the quantity of interest we are interested in. We have this asymptotic expansion here, where the first one is just the quantity of interest evaluated at the map estimators. So this is a kind of consistency result as well. What you can do then, based on this asymptotic expansion, you can basically prove that for preconditioned smaller quadrature methods, we can prove convergence rates, first of all, which are independent on the number of parameters, but which are also independent on the size of the observational noise. So on the observational noise variance, generalization to preconditioned quasi-Monte Carlo methods, as we have heard about, for example, yesterday, this is quite straightforward in the uniform setting. So the motivation for our new results was to generalize to other priors. In particular, we were interested in the log normal priors, like in our motivational example. And we want to use now the approximation results for preconditioning strategies for MCMC, so Markov chain Monte Carlo, and importance sampling. So that was the motivation for the following result. Okay, so here's the setting in which we want to work now. We have a sequence of concentrating probability measures. Here we have the scaling with respect to the parameter n, scaling the noise. We have here the normalization constants, also depending then, of course, on the scaling parameter n. This one here is just the Lebesgue density of the prior. This fractional n is the support of the prior Lebesgue density. This one here is Laplace approximation, so UN is just the map estimator, so it's the minimizer of this function here, and this one again is the second order information. Okay, so what do we need for in order to prove our approximation results? So here are the assumptions. First of all, what we need is that the misfit functional, which we denoted here by phi, and the prior Lebesgue density are smooth enough, so we assume here C3. We assume that UN is the unique global minimizer of the negative log posterior density, and necessary second order conditions are satisfied, which means basically we have that the gradient is equal to 0 and we have a positive definite Hessian at our minimizer. Furthermore, we assume that there exists a limit of this sequence of map estimators, and the same is also true for the sequence of Hessians. So first of all, I have to say that those assumptions here, the first two, are quite natural in order to show well-posedness of the Laplace approximation, so I would say this is quite natural to assume. Then we need two more assumptions. Okay, the third one is on the third order derivatives. We need this assumption in order to show that in a ball around the map estimator, just a second, in a ball around the map estimator, the difference between the posterior and the Laplace approximation goes to 0, basically, with a certain rate. Sorry.
I don't quite understand. All these quantities are random variables that depend on the data. So what does it mean to assume that they have limits? Is it for all omega, or is it in probability, or?
No, what we assume here is this one is the map estimator. So this one is just the unique global minimizer of the functional IN, which is the negative.
Maximizing the likelihood function, which depends on data. So for every data realization, your map is.
We fixed the data. That's a good point. So that I should have mentioned. So we fixed the data. So it's different in this way from the Bernstein von Mises results, which you discussed yesterday. That's different. So this one here, we have to fix the data, whereas the result you presented yesterday, this one is really on the consistency of the posterior distribution.
If you have noise, then in my probability space, I can always find some points for which the MAP does not exist. I mean, you know,
but we are in the finite.
It is possible that you have infinitely many heads. I mean. So I don't understand what it means to make an assumption when you fix the data. I mean, for these limits, it should be. I mean, if this is a statistical result, it should be a probabilistic limit here, I guess.
Yeah. So well, it's It's
Otherwise,
different.
one shouldn't speak about noise. I mean, or you have to say that noise is deterministic. But then they're like, I mean, I don't
Yeah.
really, I just don't understand. But
Yeah. So this one is this result here is in this sense different from the Bernstein, the classical results, Bernstein from Mises, which show consistency in the case where the noise goes to zero. What we want to do here is just analyze the numerical performance of our method with respect to the noise going to zero. So we have to fix the data, so it's not like a consistency result like the
that's your
Bernstein.
assumption. So your
Yeah.
assumption is that for every possible data realization that you ever see, the MAP estimate converges to a fixed function.
Yeah. Yeah. But
That's why
yeah.
this can never be satisfied in a probabilistic model. But okay, we can
Yeah.
take this offline.
Yeah, we can discuss it later. Yeah. Okay. Okay, so that's the setting in which we have to work in order to get the results. I will show you in a second. So just to explain you also the way, the other assumptions which we need. So this one here is on the third order derivative in order to approximate the difference between the posterior and the Laplace approximation, and this one here is in order to ensure that in the complement of the ball, where we use this assumption here in the complement of the ball, we can show convergence as well. So this one here is to approximate the difference between the posterior and the Laplace approximation in a ball around the map estimator, and this one here in the complement, so that we end up with the following result. We have in Hellinger distance that the difference between the posterior and the Laplace approximation indeed converges with a rate of 1/2. But I'm running slightly out of time. I'm sorry for that. So yeah, just I mentioned the basic idea. So we need all the assumptions in order to first of all approximate the difference in a ball around the map estimators. Then we go to the complement, and furthermore in the complement of the support of the prior distribution. So we can generalize everything to a singular Hessian, but assuming, of course, that we have a concentration effect in a linear subspace. No Gaussian prior assumption, we can easily incorporate numerical discretization error, so that's quite straightforward to account for this as well. And a first very straightforward implication is, of course, that we have a kind of consistency if you want to use the Laplace approximation instead of the posterior approximation, instead of the posterior as an approximation, because well, we can split the error in the approximation error stemming from the Laplace approximation, and this one here is just the sampling error, which depends on the sampling method you want to use. So usually you can bound this error here, and this one here stems from the approximation with the Laplace approximation. Okay, so to conclude now, just quickly what we did. Convergence results in order to show that preconditioning techniques can overcome convergence problems. Combination of optimization and sampling techniques might be worthwhile to consider, because with the concentration effect, the optimization methods work quite well in this setting because you have steep gradients, so it might be worthwhile to consider a combination of both. And we want to use the results in order to show that Laplace important sampling is indeed robust with respect to the size of the noise, and also for MCMC. So if you are interested in a noise-robust MCMC approach, I highly encourage you to look at Björn Sprung's poster on variance independence of random walk metropolis Hastings algorithm. Okay, so sorry that I'm running out of time. Thank you.
Questions? Somebody else? Usual suspects. All right. Okay.
So two sides of my question. So from a practical point of view, if you do the Laplace approximation, obviously if you have something that's more banana shaped, like a Rosenbrock, then and it starts concentrating and it takes a long while to contract in one curved direction, you will still suffer in practical setting. Because you only, let's assume I'm just using a one-dimensional approximation, Laplace approximation, rank 1,
Yeah.
then I'm just going to suffer from.
Yeah, definitely. So that's what I said at the end. So what we have to assume for the generalization to singular Hessians is that we concentrate in a linear subspace, so no banana shape, but still you can, of course, in the limit, you can argue in the finite dimensional settings that you will converge to Gaussian and that at some point.
If we're going now to the theory and the assumptions, since you're in the finite dimensions, I could just take the map point and just identity scale with n as my, or 1 over n as my my precondition that you could prove the same thing. I mean, where do you actually use the fact that you need the Hessian at the map point? Because your proof just needs to scale correctly, because you're assuming anyway it contracts.
So of course this is a very simplified setting, which means, so just from the model you can see that we assumed we have just a uniform scaling in front of with the parameter n. So you can think of having different convergence rates, so to say, in one part of the covariance matrix and another rate in the other. So of course this is just a very
identity would be fine. No?
Yeah, so this is just a very simplified situation where everything is determined by the convergence rate of this n here. If the n goes to 0, then this is the factor you're interested in. But yeah, definitely in practice you should account for different rates of convergence.
So I want to put out a challenge, because in information geometry, the first gain is to bias correct the maximum likelihood estimator, in which case you get faster convergence, you get 1 upon n convergence. Okay, so I wondered if there was an analog for the map estimator using these kind of methods, or in Bernstein von Mises, where you can actually get 1 upon n convergence as opposed to 1 upon root n.
Well, the convergence depends on the sampling method you want to use. If I understood you correctly, you can use higher order quasi-Monte Carlo methods if the forward problem allows, of course, and then you have a much higher convergence rate than 1 if the forward problem allows. So this convergence rate in the end depends on the method you want to use. Like, for example, if there is enough smoothness, you can use sparse grids or quasi-Monte Carlo approaches, and then you have a much higher convergence rate. Here's just the preconditioning idea in order to control the constant in front of, I have to say this. So we can't get a higher convergence rate by preconditioning by the integrand, but what we can control is the constant in front of the convergence rate. So yeah, that's a difference. So there's no enhancement of the convergence rate.
We're going to have coffee in a second. Let me finish off with one question.
Yeah.
Use the Hellinger distance.
Yeah.
Is that because, okay, so often it's convenient to use that, partially when you're working with gases. You get more stuff out of it because you can, when you integrate the product of the densities, you get 2 Gaussians. It's rescaling. Is there a reason we chose the Hellinger distance?
But it was because of the motivation. We wanted to use it in the MC framework, so Hellinger was the first choice, so to say, in order to get the results also in the MCMC framework, and it directly relates also to the difference in the mean, for example, of our quantity of interest. But in the references, I mentioned also, I didn't mention it in the talk, I should have mentioned it, this paper by Yu Long and Andrew Stewart and Henrik Weber, where they looked at Gaussian approximations for probability measures on RD using the Kullback-Leibler divergence. So there are results also for different distances. Yeah, definitely.
Let's next week.
Okay.